Assalamualaikum warahmatullahi taala wabarakatuh and good morning. I'm Dr. Sabah Bau from the Physics section, Pusat Pengajian Pendidikan Jarak Jauh, University Sains Malaysia. This is course JIF 318 Quantum Mechanics. We are in chapter 2 Complex Numbers and Linear Operators. In this segment, Unit 2.6, we will discuss some properties of linear operators. The objective of this lesson, basically, after this, you will be able to do some mathematical operation involving linear operators. Let us recall in the previous segments, linear operators occupy a central place in quantum mechanics. Basically, they are used very extensively. For any observable quantity, what is meant by observable is that the quantity which we can observe or measure. Okay. For any observable quantity O, we can find a linear operator with capital O and a head there with the following properties. If a particle is in a definite state O, that means a Stern value, specific value O, then the wave function psi for the particle is an eigenfunction of O, operator O with eigenvalue O. And the relationship is like this. So you have capital O with the head there, that is the linear operator, multiplied by psi, the wave function, must be equal to a Stern number here, which is called eigenvalue, multiplied by the wave function psi again. Okay. So there is a close relationship between the operator and the eigenvalue. The wave function psi is called eigenfunction. Note that even though capital O with a head is an operator and small o is a number, but the operator O and the eigenvalue O must have the same physical units. It depends. For example, if you are looking at position, then it must have they must have the unit for position, such as meter or centimeter. The most important thing, the unit for the operator and the eigenvalue must be the same. That is when we have specific or definite state of eigenvalue. That means small o is a number. It can be real number or complex number. The second case, if the particle is not in a state of definite value of O, then psi will not be an eigenfunction of O. If the particle is not in a state with a definite value of O, that means O is not definite, it's not specific. You can pinpoint exactly what is the value of O, then psi will not be an eigenfunction of operator O. If a measurement of the observable is made, there is no way to predict the result. You can expect the exact result. However, the expectation value of O is still a well-defined quantity. That means for a non-specific eigenvalue, then you cannot have psi as eigenfunction, because we cannot say specifically what is the value of the eigenvalue O. But we can also define an expectation value of O. That means in terms of probability. the expectation value of O or the eigenvalue O must be within this range or at this region, and so on and so forth. And this is defined as integration. Then you have the complex conjugate of psi multiplied by the O operator, O with the head there, multiplied by the wave function, and this is in volume D3 vector R. Okay, so you have two cases. If you know the exact or expect O to be specific definite state, then you have this relationship. Basically, this relationship relate the observable value O, that is the eigenvalue here, with the operator capital O with the head there. So this is the operator, this is the wave function or eigenfunction, this is the eigenvalue, and this is eigenfunction again. Okay. If in the second case, this O is not in a state of definite value, what you expect, that's what we mean by the expectation value. The expectation value of O have this relationship. That means integrate, and remember that psi star multiplied by psi is the probability density. So if you have a certain observable quantity, then we have an operator here, linear operator O, between the psi star or conjugate of wave function and the wave function. Okay. Recall again that the two properties of linear operators. If you have a derivative operator or operator of a combination of two functions f and g, then this must be equal to two operators for each individual function. Okay, such as this operator O in the square bracket f plus g. That means now we have the operator for two combined function must be equal to operator f plus operator g. That means now you can add it individually. That's the first property of linear operators. The second one, if you have an operator and a number here c multiplied by the function, then the number can be brought out of the operator operator function. So you have, for example, like here, an operator of c f equal to c operator f. So these are the two properties of linear operators, and this is for all functions of f and g and all complex numbers c. Remember that c, when I say number, it can be real number or complex number. Okay, if you have two operators p plus q, if you add them, represent them the summation as r. If operator r equal to operator p plus q, then if you multiply the operator with a function, let's say here rf, operator r f must be equal to, in the bracket, the summation of r. Operator p plus q multiplied by function f. Okay, this must be equal to separate operators. This is just like in the first properties of linear operator, except that in the properties of linear operators you have two functions, but here you have two operators p and q, and only one function, and it is equal to the individual multiplication of operator p with f and plus operator q with f. For subtraction, if we define R as P minus Q, operator R equals operator P minus Q, then RF, that means if you multiply with the function, then basically just like the addition part up there, you just basically have the difference between operator P multiplied by F minus operator Q multiplied by F. Okay, or operator Q for F of that function. If in the products operation, or sometimes it's called composition, you have operator R equal to operator P, operator Q. Then if you multiply or do some mathematical operation involving this operator with respect to the wave function psi, so the R there you can replace with P, operator Q, then wave function equal to, you can bring out one of the operator outside, usually the first one, and you operate the wave function with respect to operator Q first, then whatever you get it, then you follow up with the operator P. This is an example of multiplication of two operators. Okay. Question, let X operator X. There must be a head there, but somehow outside of the equation editor, I could not get the symbol of head on top of an operator. So you can see here that all the operator have no head except for the answer here. You have head because the answer is written using mathematical equation editor. Let operator X be one-dimensional position operator. That means position operator, and this is the relationship with a specific value. Just now we had discussed this. Operator X psi must be equal to X psi, where X here is the eigenvalue. Remember that. Okay, this is the specific or what we call as position operator. That means we are talking about position X. Small x here is the what we call as observable quantity, which can be measured in an experiment. And let operator D be the derivative operator. Derivative operator, usually it is like a differentiation with respect to what? Here it is defined as operator D psi equal to D psi per dx. That means this is the operation for the operator. Basically you are differentiating psi with respect to x, and the question asks for the value of D x, operator D, operator x. So we multiply operator D with operator x with psi equal to, now the definition given here, D is defined as, operator D is defined as a derivative or partial derivative D per dx. So we put there D per dx. Okay, x psi or operator x psi equal to small x psi. So we replace operator x psi with small x psi. Then of course we do the differentiation. If you have to what should I say, two values for the differentiation, you differentiate the first, keep the second, plus differentiate the second, keep the first. That is like pembezaan bertingkat. Okay, you differentiate one by one. So you differentiate x, dx per dx, of course equal to 1. Keep the second, that means 1 multiply psi, you have psi here. And you differentiate the second, basically d psi per dx, and keep the first, this is x. That means now you have psi plus x d psi per dx. Okay, if we bring out, you can see here that d psi per dx is actually the operator d, and small x is related to operator x. So you have 1 plus operator x, operator d, the whole thing multiplied by psi. So what do you see here is that your multiplication of operator d and operator x will not give you operator d multiplied by x, because here it is related to 1 plus operator x d. That means the relationship is here. In other words, it's not commutative. That means you cannot just put the position of two operators randomly. It must be following certain sequence. For example, if operator d and operator x is not equal to operator x multiplied by operator d. This is the proof that multiplication of two operators, such as shown in the example, might not be commutative. That means you cannot place them anywhere you like. It must follow certain sequence. In conclusion, mathematical operations such as addition, subtraction, and multiplication can be carried out on linear operators. And this operation is used in quantum mechanics. Thank you very much for your attention.